Obviously, we missed a day, and everybody missed a day, and my morning class missed 2 days, and they won't meet again until next Tuesday, so things are a little bit out of sync. How many of you did get and read either my email last night or my post to D2L last night? Okay, so you know then that we are on a modified schedule. I sent that schedule out. I just want to give a couple highlights on that. And just so I can kind of get a check on this, how many would and I'll do it, I'll provide a printed copy. How many would want a printed copy? Just kind of, okay. I don't have one today, but I'll bring one in here then next Tuesday. And that way when I print it out, I'll have it printed out for both my morning class and my afternoon class. And I'll just get it then for everyone. But we have a modified lecture and exam schedule. The exam that was scheduled for the 5th has been moved up to the 7th, in part especially to accommodate my morning students because they will have missed both of their classes this week. They are going to be expected to do some stuff on their own here for today. I will be posting my lecture notes and video, and they'll be able to do that, kind of catch them up. And then everything basically in the schedule is delayed by one class period. And one of the things about the spring schedule is that I have 3 extra class days in here that I didn't have in the fall semester, and so I did have some room to play with here anyhow. One of the things I had to play with and what got eliminated was the review class that we had scheduled here a week before finals. Now, you might say, oh, well, I really need review. Well, the Academic Support Center does provide review sessions during that week anyhow, and so that's what we have moved on out. So every exam on there has been delayed one class period. I understand that some of you may have made schedules that were based on what published before. I got one email saying, hey, I'd already planned a trip to be gone during that. I can't be inflexible because of that. However, one of the things that I will note here, and blah, 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 is this written here? No. Still, there will be no late makeups. So if it's an exam, though, the moving of the exam date that has created a conflict, you should know that conflict ahead of time because I've published it. And if there's a conflict, you need to let me know at least a week in advance of what that conflict is. Not a week in advance of the date, but a week in advance of which you would like to take that exam. So if you let me know the day before that, hey, I want to take my exam early and take it tomorrow, that's not going to work. So again, if you are going to have a conflict, you should know what those conflicts are, whether it's a school-sponsored activity or a conflict with a sincerely held religious belief or perhaps a trip that you had planned before we had changed this. I will have to accommodate those there, but there's still no late makeups on the exam. So if you happen to be sick, get a flat tire on your way to school or something like that, those are still going to be ones where you'll take a 0 on it, but understand that it will be your dropped exam. So any questions on that? Any questions? All right. So what we are covering here today will be what was supposed to have been covered on Tuesday. And what else? Oh, lab schedule. The lab schedule has been modified as well. Those of you that are in the Wednesday lab section, you have the greatest modification to your schedule. Those that would have had lab yesterday, you will be doing lab. The lab you're supposed to have done this week, next week. So basically, if you look at this, the new ones here in red, and the ones that aren't crossed out will be the new schedule. So again, this is published to D2L. I will have a printed copy out here for you of the revised lab schedule next Tuesday as well. So any questions on either the modified lecture or lab schedules? And if you do have the Wednesday lab, I'm sure those aren't up. Who teaches the Wednesday lab? Peeper? Okay, she was just in here. She knows she has to modify those and everything. She'll be modifying the dates in there. This all takes time. These things don't update automatically. Likewise, the due dates and everything I talked about, they don't update automatically. One of the things you're going to find, if I were to go back to the due dates in here for chapters 3 and 4. And again, this is large part due to the morning students that are missing. I have modified the due dates for all of the practice problems and the Mastering Chemistry homework quizzes as well. So these are what the dates look like. However, if you logged into D2L or into Mastering Chemistry, you're going to see that all of the due dates for 3A, 3B, homework quiz 3, 4A, 4B, and this all fall on February 6th in the system. And that's in part because for those missing the lecture here in the morning, and maybe even some of your peers that are missing today, it may take a little while getting caught up on everything. So everything's been moved to this date. If you wait until that date to do it, you're probably not going to get it all done. So this is what the intended schedule would have been in the modification. So if you stay on this timeline as shown here, then you should not feel overwhelmed by everything that has been moved to a due date of the 6th. So any questions on that? All right. So I think that takes us into what we need to cover here for today. We have the Socrative app question that's waiting for you. You register with your chemical symbol. Oh, element quiz. Element quiz is on D2L. That will open up today after lecture. I will talk a little bit about the expectations here for that after we are done with the I don't even remember what to say, but we'll discuss it here at the end of the hour today as to what those expectations are. All right? So with that, let's go ahead and look at the Socrative app question. This one here, pretty straightforward. You had a 50-50 chance if you just guessed. Hopefully you didn't just guess. We talked about ice melting. Ice melting would be an example of, I love to start off that way, as an example of a physical change. And even though we did get to this last week, let's see how well your notes are, or how well you can reason this one. This is the last one we did on Thursday, a week ago. Solutions of sodium hydroxide and hydrochloric acid are mixed, causing the temperature to go up. This here is an example of, let me count down, 5, 4, 3, 2, 1. This here is an example of a chemical change. So with that, what we're going to do next here now is a tape demo. And for those listening at home, I'm going to put the tape demo up in a separate demo. So if you want to review this at home, I did the recording here this morning in my office. I need to do a voiceover of it yet. I'll do the voiceover this afternoon, and then I'll post that demo up in addition to the notes here from today. So at the end of the bench here, I've placed some piece of tape. And if you're sitting at the end of the row, you are the demonstrator for that row. So if you're not at the end of the row, somebody in your row needs to move down to the end here. And there's a couple pieces of tape there that are waiting for you. And I'm going to put my own piece of tape here up on the front end. And this here is just ordinary Scotch tape. And I'm just putting them down to the table. And of all days to do this, we have picked the best day in the last 23 years to do this demo. And the reason why it's the best day is because this demo works the best when the air is really dry. And you're never going to have any drier air than it is when it's extremely cold outside. So the demo that we see today, it will always work whenever you try it, but it's never going to work as good as it is today. So we're here on a very special day for this demo. So now what we're going to try to do here is we're going to demonstrate how charges interact with each other. We have charges that are positive and charges that are negative. And whenever we have friction that occurs, you've probably even noticed here the last couple days as it's been really cold, if you're walking over a carpeted surface, you might think that you're not dragging your feet at all, but if you approach something that's metal, what's going to happen? and get a shock. And I mean, even at home, I know I touch my cats and everything, and I've been giving them shocks like crazy and everything, because even just like moving across the bed sheets or something like that is enough to, in the super, super dry air, enough to pick up a static charge. So whenever there's friction, even walking across this floor here, dragging your heels a bit, you're going to pick up a little bit of static charge. And the static charge, when you pick that up, is due to the transfer of electrons. And electrons have charges that are, anybody know? They're negative. Electrons are negatively charged. And we'll talk about tomorrow why it is electrons that are transferred and why it isn't protons. But now, when we rip these pieces of tape up off the table, we're going to cause a transfer of charge to take place. And you think, having done this 30-some years, I know which direction charge moves to this day. I still don't know which direction the charge moves. But it doesn't really matter which direction it moves. Because what's going to happen, and don't do this yet, is I'm going to grab onto the handles. I should have made some handles on this piece of tape for you to grab on the end, so it doesn't stick to the table. I'm going to rip them up off the table. When I rip them up off the table, that's going to cause a transfer of charge. Now, let's say that the table is something that transfers electrons to the piece of tape. The table transfers electrons to the piece of tape, then both the pieces of the tape will have acquired a charge that is negative. Now let's say I was wrong. Let's say instead that the table is something that takes electrons away from the pieces of the tape. If I rip it up and the table takes it away, at the end the piece of tape will wind up charges are positive, but what's going to be really important is we're going to notice that the charges of the two pieces of tape should be the same. So again, if I rip it up and the table gives off electrons, they wind up with the same charge. If I was wrong and said that the table takes away electrons from the piece of tape, the piece of tape are still going to wind up with the same charge relative to each other. So let's go ahead and grab the handles here on the piece of tape, and if you're sitting on the end, grab your handles, because you're the demonstrator for the row, and go ahead and rip them up off the table. Once you rip them up off the table, they might stick to your hands or whatever. Pull them off your hands or fingers, and then you can hold the piece of tape and then bring the two pieces of tape next to each other so the people in your row can see. Notice what happens to the two pieces of tape. And what's happening to them? Are they attracting each other or are they repelling each other? They are repelling each other, exactly. So now, they are repelling because like charges will repel each other. So now, take the two handles, pass them down to another person in your row, give them the handles. And now what we'd like to do with these pieces of tape is we want these pieces of tape to acquire opposite charges. We want them to acquire opposite charges. Any idea how we can get them to acquire opposite charges? Well, here's how we do it. What we're going to do, and make sure that you leave your handles here, we're going to stick the two pieces of tape together, and you could put them sticky side to sticky side. That just makes them hard to rip apart. So we're going to stick a sticky side to a smooth side, and just like this. So you have the two pieces of tape together, we'll leave the handles. Now, before we rip them apart, understand that if we rip them apart, if one piece of tape loses electrons, the other piece of tape will gain electrons. The two pieces of tape should have charges that are opposite of each other. So go ahead and take them, rip them apart. If they're sticking to your fingers or whatever, you can pull them back from there. And then if you put the two pieces of tape next to each other, notice that the two pieces of tape will attract each other, which tells us that opposite charges will attract. Now if you think this is some gimmick, pass it down to another person in the row, or pass it back if there's only two people. Let's go ahead and put them back down on the table again. Just smooth them down, leave your handles off the end, rip them up. Now remember, we're now treating them both the same, which means they should have like charges. If they have like charges, you bring the two of them together, the two pieces of tape will repel each other. So again, what this shows is that opposite charges will attract, like charges will repel. So remember that lesson. So if you're going to forget it, write it down. Opposite charges will attract, like charges will repel. Now, the maintenance department, they don't like to find these things attached to tables and chairs or on the floor or whatever else. So either put these in your notebook or in your pocket, or I'll give you about 30 seconds to run up to the trash, either in the front or back, and throw them in the garbage. But please don't leave them on the floor, the tables, or anything else in here. Okay, so again, what we found out is that opposite charges attract, and like charges repel. All right. Any questions from our chemical change versus chemical change demos last week? Anything we need explained? Okay, then, on your handout there, if we move down to chemical property and physical property, talk about a chemical property. These here may be observed when there's a change in chemical composition or an attempt to change the chemical composition. So again, these are the types of properties that are observed whenever there's a change in chemical composition or an attempt to change the chemical composition. In other words, we don't actually have to change the chemical composition in order for it to be a chemical property. We just have to be attempting to do it, and if it doesn't work, it's still a chemical property if we say that it doesn't react with something, for example. Whereas a physical property would be defined like this. We say that this may be observed when there's no attempt to change the chemical composition. So let's give a couple of examples. Let's say that iron rusts. Iron rusts. Iron rusts would be an example of a chemical property. The fact that it rusts, again, that is a change in chemical composition or an attempt to change it. Let's say that we talked about chrome. Chrome. And chrome is a mixed alloy of several different metals. But if we said that chrome does not react with oxygen in the air, that would be an example of a chemical property. Even though it doesn't react, the fact that we're talking about it or attempting to do it would be an indication that it is a chemical property. We said that the boiling point of water is 100 degrees Celsius. That would be an example of a physical property. Because if we boil it, just like I think we did here the other day, boiling is an example of a physical change, and we're not trying to change the composition when we boil the water. So if I were to give a couple more examples here, here's the ones that you can do for yourself. Check your knowledge on. We said that the density of water is 1.0 grams per milliliter. The density of water is 1.0 grams per milliliter. We get our answers locked in on this. Count down. 5, 4, 3, 2, 1. This would indeed be an example of a physical property, because measuring the density, we just need to know its mass and its volume. We don't need to change it into anything else. If we said that hydrogen is explosive in the presence of oxygen gas, this here would be an example of, count down, 5, 4, 3, 2, 1. We find out that that is a chemical property. So very good. Moving on. Are any questions on either of these or on them in general? Okay, so now moving on here. When we did some of our demos last week, we talked about some of the changes that occurred as either the temperature going up or going down. These relate to the amount of energy that is either absorbed or released. If we talk about thermic, what do you suppose thermic refers to? Thermal energy, which is another way of saying heat. Okay, and how might we observe heat or the lack thereof? Yeah, but what do we look at? What would be an indication that something has more heat than something else? The temperature, exactly. So when we look at these processes, the prefixes endo and exo also mean something. Exo means outside or going out. Endo means inside or going into. So we say that an exothermic process, this here is the release of energy. And usually we think about it as temperature change occurring. So we say that this is a release of energy to the surroundings. Whereas an endothermic process is the absorption of energy from the surroundings. Now there's a couple terms in here that I am emphasizing. First of all, it's release and absorption, and then the surroundings here. Because we'll find out later on in this course, we're going to make a distinction between the system and the surroundings. And the system and the surroundings are not the same thing. Now the reason I bring this up is because typically, when chemists talk about something, we want to know what happens to the system. When we look at a chemical reaction, that's a part of the system. But you and I are never a part of the system. You and I are always a part of the surroundings. We're the ones looking in as outside observers to something else, and we want to tell what's happening to that. Now, where that's important is that whatever we observe is happening to the surroundings is just the opposite of what is happening to the system. Okay, so if we talk about this being an exothermic process, which is a release of energy to the surroundings, what do you think is going to happen to the temperature of the surroundings? Temperature is going to increase. And if it's an endothermic process, where we say it's an absorption of energy from the surroundings, that means that the temperature of the surroundings is going to decrease. So whatever you and I observe, we are always observing as to what's happening to the surroundings. Whatever is happening to the surroundings is just the opposite of what's happening to the system. So if there's a release of energy to the surroundings and the temperature goes up, that is, the surroundings have more energy, that means that the system actually has gone down in energy. And if we have absorbed energy from the surroundings, that means that the surroundings would have gone down and that the system would have gone up in terms of energy. So whatever happens to one is just the opposite of what happens to the other. But you and I are always a part of the surroundings, but we are always trying to describe what is happening to the system. Whatever is happening to the system is just the opposite of what we observe here in the surroundings. Okay? So if we observe the surroundings increase in energy, that means that the system has decreased in energy. Okay, so that's going to be one of those things to keep in mind, that when we go through this later on in the course, you're going to say, well, this doesn't make sense. I thought we talked about exothermic being release of energy. Why doesn't it have more energy? Well, it doesn't have more, the surroundings do, what you and I are observing, but that means it has to come from somewhere. And the somewhere it's come from is the system itself. Okay, so any questions on that? Okay, and I think that takes us then into chapter 4. In chapter 4, it starts talking about how we classify matter. And when we classify matter, we break it up into two broad categories. And this is the figure that's in your text. If you don't have your textbook here, I can zoom in on that. That's okay. I can zoom in on it a bit here. But we basically break down matter into two broad categories. We break them down into pure substances and mixtures. So again, we break them down into pure substances and mixtures. When we talk about something being a pure substance, this is actually kind of redundant to a scientist, because when a scientist talks about a substance, we are talking about something that is pure. So when we use the word pure substance, that's only for students, when we put the word pure in front of it. When chemists talk to each other and we talk about a substance, we're already talking about something that is pure. All right? So if you see the word in your textbook, substance, that really is referring to something that is pure. And what we say then is that a pure substance is something that has a definite composition. Its composition is known. Whereas mixtures over here, these are things that can have a variable composition. So now if we were to kind of base it on this right here and look at one term based on these very basic definitions, which of these items, A through E, would be classified as a pure substance? And feel free to talk to your neighbor, as always. Ask yourself, is it pure or is it a mixture? Okay, I'll give you about 15 seconds to lock in an answer. Countdown, 5, 4, 3, 2, 1. Correct answer here is indeed deionized or distilled water. If we talk about deionized or distilled water, that's the stuff that comes out of, if you go in the lab, it's out of the plastic, gray plastic taps. This is purified water, it's H2O. There's nothing more definite than talking about water having 2 hydrogen atoms for every 1 oxygen atom. When we write a formula for water, its formula is H2O. And so it's definitely a pure substance. Air is not pure. Air is a mixture. And what is it a mixture of? Anybody know what the most abundant component of air is?
Nitrogen.
Nitrogen, yes, it's nitrogen. Second most abundant. Well, what the heck do you guys need to survive? Oxygen. Now, many people mistakenly think that oxygen is the most abundant substance in the air. It's not. In fact, 78% of the molecules in the air are actually nitrogen. Only 20% of the molecules in the air are oxygen. Okay? In addition to that, we have carbon dioxide. That's the third most abundant in there. Fourth most abundant is water vapor. And fifth most abundant is argon. Surprise, surprise, it's argon. So air is actually a mixture. Honey is also a mixture. This isn't pure. You like to think it's pure, especially if you get like organic honey, but honey is really sugar dissolved in water. Sugar dissolved in water, so it's a mixture of sugar and water. So if we come back to our diagram here, talks about these, breaking them down a little bit more. We talk about pure substances. Pure substances consist of elements and compounds. Elements and compounds. And of course, where do we find the elements? Periodic table, exactly. So if you come back to the periodic table, which I passed out here, these here are the elements. We know today of 118 different elements, and that's it. And then if we combine these elements together in fixed whole number ratios, then we wind up with what we call compounds. And so an example of a compound would be something like this. Water is an example of a compound. Water is one of them. Another one is what's shown right here. These are sugar cubes. So sugar here, this would be something like sucrose, sugar. And anybody happen to know the formula, not of glucose or fructose, but the formula of sucrose? Now I know you know glucose, most of you do. It's C6H12O6. That's not sucrose though. Sucrose is C12H22O11. And then of course, this stuff here. Most of you know what this is. This is salt. In terms of its chemical composition, it's NaCl, which is a name of sodium chloride. Very good. So NaCl, or salt, would be an example of a compound. So in these here, when we write out these formulas, these are formulas for compounds now. They have a very definite composition. These here represent molecules of sucrose, the C12H22O11. For salt, its formula is NaCl. This here is actually what salt looks like, sodium chloride. We find it in cubes because, and a 1-to-1 ratio is what this formula represents. 1 sodium for every 1 chlorine. Sodium's here represented by the small spheres, the chlorine represented by the large spheres, and of course H2O, which is the formula for water, showing the 2 hydrogen atoms for every 1 oxygen atom. Okay, then over here on the mixture side of things, we have homogeneous mixtures and heterogeneous mixtures. The prefix homo stands for alike. Hetero means different. So when we talk about a homogeneous mixture, that is a mixture which when you look at it, and I don't know that I have any with me here today. I did not bring any in. But if I go back to a sugar solution, if I dissolve sugar and water and mix it together, if I showed you a sugar solution, you looked at it, you would think that sugar is comprised of one substance. Okay, just like some of you maybe thought that honey was a substance. You look at it, it's clear and whatever, it looks like only one, but actually honey is a mixture of sugar and water. So, but that's one, when you look at it, a homogeneous mixture is if it appears as if there's one, there's actually multiple substances in there. In a heterogeneous mixture, again, the prefix hetero means different, and so when you look at it, you can very clearly tell that it's a mixture of things. So if you looked at some sand or a tossed salad, you'd very, very quickly be able to see that it's a mixture of different things. Okay. And then from here, we're going to end, I guess this is still chapter 3, we're going to end chapter 3 with a look at temperature conversions. And to do temperature conversions, you're going to flip your periodic table over and look at the conversion side. And looking at the conversion side, you have a number of temperature conversion formulas listed over here. These temperature conversion formulas, these are exact. And again, what does it mean if they are exact? Infinite number of significant figures, exactly. So this could just as well say 5.000 on into infinity over 9.000 on into infinity. And then in parentheses, this would be the Fahrenheit temperature minus 32.000 on into infinity. So again, these are exact conversions, which means they have no impact at all on significant figures. So with that in mind, I'm going to give you some conversions I'd like for you to do. They are, let's convert a temperature of 25 degrees Celsius to a temperature of kelvins. Let's convert a temperature of minus 40, since we got so darn close to it here today. Temperature of this morning, my thermometer is minus 34. And let's convert this to Celsius. And then let's take a temperature of 37.0 degrees Celsius. And let's convert this to a Fahrenheit temperature. So I'll give you a few minutes here, maybe 5 or 10 minutes to do these. And you can help each other out, work together. And you're using these conversions right here, all of which are exact. And these are going to show up in order on the Socrative app. Committing yourself, remember significant figures. When you give your answers, they must have the correct number of significant figures. Maybe about 2 more minutes. The first one is already up on Socrative? Help each other or ask questions of your neighbor if you're not sure. It'll take about 30 more seconds for the first one. Okay, and we'll count down on this one. 5, 4, 3, 2, 1. Correct answer here is shown by about half of you, which is 298. 298 is the correct answer. So 298. Now the reason for this is if we come back here and sum these together, we take 25 and we add it to how much? 273.15. We add it to 273.15. This, of course, here is exact, but 25, remember when we add and subtract, we don't look at significant figures, we look at decimal places. How many decimal places does this one have? 0. So if it has 0 decimal places, that means our answer should have how many decimal places? 0. And so again, that's because this digit here, the ones place, is the uncertain digit. That means that the ones place is uncertain out here, and the answer would write it as 298K. Next up, and by the way, how long do we have to pay attention to significant figures in this course? Always. Forever and ever, till the very end. Okay, next up, negative 40.0 degrees Fahrenheit is equal to how much in degrees Celsius? This may have even been in the news. I know I read it a few times on Facebook the last couple days, the answer to this question. So we'll give you about 15 seconds to lock in an answer on this one. And if we count down on this one, please. If we count down, 5, 4, 3, 2, 1. Correct answer is negative 40.0. Negative 40.0 if you want the correct number of significant figures. Negative 40.0. Why would we have heard about this? It's the only temperature at which the two of them are equal. This is the crossover point of the Fahrenheit and Celsius temperature scale. It is the only place at which the two temperatures are equal to each other. Now if you're looking at the formula for this, we are trying to calculate degrees Celsius right here, correct? So it's 5/9 times the quantity of the Fahrenheit temperature minus minus 32. So let me write it down so before I forget it. It's equal to 5/9 times the Fahrenheit temperature minus 32. Remember now that this formula is exact. So if it's exact, we'd take, first of all, negative 40. We'd substitute that in. Negative 40.0 minus 32. If we calculate this out, negative 40 minus 32 is equal to negative 72.0, because remember, this is an exact formula. As an exact formula, this has an infinite number of significant figures. So it's actually 32.0, even though we don't write it, it's 32.000 on into infinity. So it'd be negative 72.0. We then multiply this by 5/9. If we multiply it by 5/9, we wind up with negative 40.0. And that's where we then round off to 3 significant figures, because this number here has 3 significant figures. And then if we look at the next one, (37.0 degrees Celsius). You are now traveling in a foreign country. And you're feeling sick. Say, go to the doctor. And you find out that your body temperature is 37.0 degrees Celsius. Which, of course, if we lock in our answer, 5, 4, 3, 2, 1, we found out that 37.0 degrees Celsius is the same as 98.6 degrees Fahrenheit. Which, of course, would be what? What does 98.6 Fahrenheit represent? Normal body temperature. Or what's normal for most people. Average, I'm going to say normal. Some have an average that's higher, some have an average that's lower. 98.6, so this one here, you need to remember to follow your order of operations. Your formula here says we calculate that Fahrenheit temperature by taking 9/5 times the Celsius temperature. So 9/5 times the Celsius temperature plus 32. So if we're following the order of operations, which operation do we need to do first? Which one? Multiplication. So multiply by the Celsius temperature, which is 37.0. 37.0 times 9 over 5 is going to give us 66.6. We then add to that 32. This is going to have an infinite number of significant figures, so if we sum these two together, we wind up with 98.6. And again, that's because this is 32.000 on into infinity. Any questions on any of these? All right, that does take us then into Chapter 4. In Chapter 4, we take a look at atomic theory. And when we talk about atomic theory is basically telling us how we get to the idea of the atom the way we know it here today. And so we say that the first modern atomic theory, and I'm going to put modern in quotes, based on scientific evidence, was proposed by John Dalton in about 1808. Now, just so you know that when it comes to tests, I don't test names and dates. I just write them down to give credit where credit's due. Rather, I'd prefer that you know which experiments proved what. And in the case of Dalton, if you were to look through Dalton's atomic theory, and I don't have my textbook here, well, I do have it, but I see that you have your textbook here all of itself. We'll talk about Dalton's atomic theory in your text on page, and this is in Chapter 4 now, talks about this on page 100. And in here, if I read these to you, you don't need to write these all down, okay? But if you listen to what his atomic theory says, here's what Dalton had said. First of all, he said that each element is composed of tiny, indestructible particles called atoms. Okay? Now, he named them atoms because he named them in honor of a Greek philosopher named Democritus, who had come up with this idea like about 2,000 years earlier than him, and described, if we say took a piece of wood and cut it up into smaller and smaller pieces, it eventually get down to a point and you couldn't cut up that wood into any smaller bits, and described that as atomos. And in Greek, atomos means non-dividable or indivisible. And so that's kind of where it came from. And when Dalton named it, he named it then in honor of Democritus, who had come up with this idea a couple thousand years earlier. The problem is that Democritus was a philosopher, not a scientist, and he philosophized about the idea. He didn't actually have evidence that such a thing had existed. Now, another piece of Dalton's atomic theory reads like this. It says, all atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. So, for example, if we were looking at a reaction of hydrogen and oxygen together, according to Dalton, all of the hydrogen atoms would have the same mass, all of the oxygen atoms would have the same mass. Now, today we know that that is not true. Okay, but all the evidence at the time of Dalton showed that it was true. But here's the biggest piece that Dalton had used in the development of his atomic theory. And if you're going to write something down, this is what you should write down. And it says that atoms combine in simple whole number ratios to form compounds. And that was the biggest piece of evidence that he used, that atoms combine in simple whole number ratios to form compounds. Now, how he based it was like this. He used evidence from what is called the law of definite proportions. In fact, the law of definite proportions basically showed that statement number 2 and number 3 were correct, according to Dalton. And what was observed was this, and we use an example. If we had taken some water from anywhere in the world at the time, when that water was studied, what was found is that that water was comprised of 8 grams of oxygen for every 1 gram of hydrogen. So what Dalton had found is that water is comprised of 8 grams of oxygen for every 1 gram of hydrogen. And again, it didn't matter where in the world the water came from, whether it came from Europe, he was from England, or whether it came from Africa or across the ocean from America. It all had that same composition, that there was 8 grams of oxygen for every 1 gram of hydrogen. Now, where Dalton had it wrong is that he thought that the formula for water was HO. So today we know that it's H2O, but at the time Dalton had thought that it was HO, and that an atom of oxygen was 8 times heavier than an atom of hydrogen. But let's look at the periodic table today. What do we know if we look at the periodic table? How does the mass of oxygen compare to hydrogen, what we know today? Approximately what ratio? And what would we even look at? The atomic mass. If we look at oxygen, we see today, we know that oxygen has a mass, relatively speaking, of 16 to hydrogen of about 1. So today we know that the ratio mass is 16 to 1, which in a couple years of Dalton making a statement that it was an 8 to 1 ratio, we found out that it was actually a 2 to 1 ratio because an atom of oxygen was actually 16 times heavier than an atom of hydrogen. So it was just a few years later then that this formula was modified from being HO to H2O to account for this 8 to 1 mass ratio. And that was simply by at that point then they were starting to combine different elements together to make compounds or decompose them, taking compounds and decomposing them to the elements. Another big component of Dalton's atomic theory was what's called the law of multiple proportions. In the law of multiple proportions, if we were to give an example, one example of this is that there are 2 two known compounds consisting of carbon and oxygen. So again, this is at the time of Dalton. I'm saying there are, I could also say there were. In compound 1, here's what was found. In compound 1, found out that compound 1 had 8 grams of oxygen for every 3 grams of carbon. And in compound 2, there was 4 grams of oxygen for every 3 grams of carbon. Now, if we look at these two ratios, how do these two ratios compare to each other? How do these two ratios compare to each other? You know what a ratio is, right? So how does this ratio compare to this one? 8 to 3 compared to 4 to 3. How does it compare? Simple question. How do they compare? Which one is half? Right, this one here is half of the first one. It's exactly half. Or we could say that this one here is twice as big as the other one. Okay? And it's not 7.9 to 3, it's not 8.1 to 3, but it's exactly 8 to 3 and 4 to 3. So if this is exactly twice as big as this one, we could say that compound 1 has twice as much oxygen as compound 2. So if we now look at it in this context, that means that if this one over here is written as CO, then this one over here should be written as CO2. Exactly. And so it turns out that this is the mass ratio in carbon dioxide, and this is the mass ratio in carbon monoxide. And so to Dalton, this pointed out that the only way we could describe this is if we had atoms. It wasn't like we were be able to infinitely divide them up. We had to have some finite things that we were putting them together. That in one case we had a 1-to-1 ratio, in another case we had a 2-to-1 ratio. It wasn't like a 1.9 ratio. It's exactly a 2-to-1 ratio. So the only way that Dalton could account for that then was to describe them in terms of atoms. So with this, if we were to kind of combine together today things that we learned about the composition and the stuff here about the laws of definite multiple proportions, that then is going to take us into our class on Tuesday. What I'd like to wrap up the hour with here today is your element quiz and your expectations. So any questions before we go on about the element quiz and your expectations? Okay. First of all, this portion is not on the element quiz, but you will have to know some things about the layout of the periodic table. And these are some vocab words that we will be using. First of all, we have the words group and period. Group and period. So if we talk about groups, these here are your vertical columns. The periods here, these describe your horizontal rows. So your groups, these are things that are labeled at the very top. So we say that this is group 1, group 2, group 3, group 4, and so on, all the way up to group 18. And then this is even labeled on your periodic table. These are your periods. This is period 1, period 2, period 3, period 4, period 5, and so on. Now you will see that there is a double asterisk and single asterisk here. Single asterisk, that means that these here are part of period 6. The double asterisk means that these here are part of period number 7. Now there's some piece of terminology that we use for these different groups. First of all, and I'll zoom in a bit on this here so we can see a little closer. If we look at group 1A, group 1A consists of elements that we refer to as the alkali metals. Alkali metals. In group 2, these here are what we refer to as the alkaline earth metals. The alkaline earth metals. And skipping on over to group 18, group 18 here, these are what we refer to as the noble gases. Group 17 is what we refer to as the halogens. We call them the noble gases because they are chemically inert. They tend not to react with anything. So we've learned today that krypton can react with fluorine, and xenon and radon can react with both fluorine and oxygen. But for a large part, they are still considered to be chemically inert. Halogens are called that because the word halo typically means brilliant or glowing. And so it turns out that the elements of group 17 are very colorful elements. And if we went back to the alkaline earth metals and alkali metals, these here, when we find them in compounds, these are very alkali or alkaline in nature. And that's another word of saying basic. And so we talk about acids and bases. These compounds, these elements here, tend to form a lot of bases, materials that are alkaline. Now, going down the periodic table, let's locate the staircase. Anybody know what the staircase does right here? Not the transition. Separates metals from nonmetals. Good. Separates metals from nonmetals. So to the left of the staircase, we find, whoops, to the left, these here are metals. To the right of the staircase, we have the nonmetals. Turns out there's one element, though, on the left-hand side of the periodic table that is a nonmetal. Anybody know which element is the nonmetal on this side? It is hydrogen, exactly. So right up here, hydrogen is the only nonmetal in the left-hand side of the periodic table. So when we talk about the alkaline earth metals, or excuse me, the alkaline metals right here, they actually begin with lithium and go on down. They do not include hydrogen. Okay, so we say group 1 is actually the alkali metals plus hydrogen. And then we have some elements that lie to the immediate right and left of the staircase. Try to highlight these. And I'll highlight all of them to the immediate left and right, with the exception of aluminum. If I highlight these elements have some metal-like properties and some non-metal-like properties. We call these the metalloids. These are the metalloids. And some metalloids have some metal-like properties, some non-metal-like properties. Now I brought one such metalloid out here. This is Si. Si is which element? Not silicone, silicon. Silicone's a non-sticky material, but silicon, you can go ahead and pass this around. You can start in the front, get to the back, and pass it forward. That's silicon. And you'll see it has the brilliant metallic luster, but it is not able to conduct electricity by itself. So again, these here are the metalloids. Going across the center here, these that are labeled with the B groupings. Look at the B's right up here. These elements are called the transition metals or transition elements, either or. transition metals or transition elements. And if we come down here and look at these are what we refer to as the inner transition elements. And these are also often referred to as the rare earth metals. If we looked at the elements, starting with the element lanthanum right here, and going across, these are elements that we refer to as the lanthanide, or the lanthanide series. So either the lanthanides or the lanthanide series. And then the ones that start here with the element actinium, these are often referred to as the actinides, or the actinide series. And again, they begin with the element actinium. Those that are labeled with the A groupings, if we come back up here, the A groupings, I'll put those here in, let's see, different color. Let's, how about orange? A groupings right here, and these right here. These are ones that we refer to as the main group elements. And generally, when we talk about the main group elements, if you pull out one element that is a part of those groups, then we find out that all of the other elements have properties that are characteristic of that one element. So again, typically within the main group elements, anything that's in that same group will have very similar chemical properties. So from here, I'd like to talk about the expectations of what you're supposed to be learning. We did mention these already. You should know two things. Let's review what they are. Somebody did ask this on the discussion board, so let's review the two things that you need to know. The symbol with proper case, exactly. So you need to know the symbol, proper case, and name of the element with correct spelling. Those are the two things you need to know. Name of the element with correct spelling and proper case. Now, there's some elements that give students fits. Let's talk about them. Here's the most commonly misspelled element right here. Most commonly misspelled element is the element with the symbol F, which is, and most of you are going to pronounce it incorrectly. If you pronounce it correctly, that'll help you with the spelling. It's pronounced fluorine, not fluorine, but fluorine. And that's because it's spelled F-L-U-O-R-I-N-E. Most people spell it like flour, like you're baking. It's not F-L-O-U, it's F-L-U-O-R-I-N-E. It'll help if you pronounce it like flu, like we have the flu, which is spelled F-L-U. So fluorine, not fluorine. So it's F-L-U-O. Commonly confused elements. These two are commonly confused with each other. They are Mg and Mn. And I'm kind of running a little bit out of time here, so maybe we'll pass these around in the next class. I have samples of both. Mg is magnesium, Mn is manganese. So again, know the two. Also commonly confused are these two, CO and Cu. CO is cobalt, Cu is copper. Any idea where we get Cu from, since it doesn't even have the letter U in the word? It comes from the Latin word, exactly. The Latin word for copper is cuprum. Cuprum. And so there's a few others that are like that, like Na comes from natrum, K from catrum. So those are some things. And this one kind of makes sense if you want to attach Latin words to them. Pb. Pb is the symbol for lead, but it comes from the Latin word plumbum. Plumbum. Now, here's why it should make sense. Now today, when they build houses, they're made out of PVC. Back when my house was built, they were made out of copper. But many, many years ago, these things were made out of lead, and we call it plumbing. We call it plumbing. Okay, plumbing. And that's because at one point they were made out of leads, and that's why they talk about getting hit by a lead pipe. That's where it came from, because it used to be that they were made out of lead. But then we discovered that lead gives people lead poisoning. And of course it makes you do all sorts of bizarre things, get mental illness, die, get sick, seizures, whatever else. So we don't like that. Sometimes it helps to have little sayings that go with things, like, what are doctors for? To heal you. All right? Or you might say, what are the last words of a dying person? Iodine. And what do you do with the dead person? You bury him. Okay, so sometimes you get little tricks like that. Or, this is my favorite. Hey, you! It's gold. Ah, gee, it's just silver. All right? Hey, you! It's gold. Ah, gee, it's just silver. All right. So with that, that is it here for today. We will pick up next Tuesday.